This video is the second part of the explanation of the topic pumping installations. In the first part we saw the operation of the pumping line and pumps in parallel and in series. If not you've seen yet, do not start this video. First go to this website if you've seen it. Let's start with the second part where we'll see installations with common point regulation of flow. Not all installations are as simple as the previous video. Usually pumping installations consist of one or more pumps to provide flow to one or more tanks. Taking of one or more tanks. Later we will see how the installations may have more complex provisions. In a first example, we will have 3 tanks. Tank 1 that will provide flow to the tanks 2 and tank 3 through the pump. After the pump, the system divides into 2 pipes, that is, the common node, on one hand, will flow to tank 2 and the other side will flow to tank 3, being Q1 equals Q2 plus Q3. Every wafer has losses, singular and linear L1, L2, L3. The method of solving this problem are 3 steps that are a little confusing, so we will explain simply and slowly. Before we have assumed the direction of the flow, this direction may not be correct. The first step would be to represent all common node curves by branches. The procedure consists of the installation divided into as many parts as pipes out of the node, and applying the energy balance. For example, in this case, node gets 3 lines. Then the installation stay divided into 3 parts. The first part would be from tank 1 through the pump to the node. Using the energy balance is obtained as the height of the node is equal to the height provided by the tank plus the pump less losses. A second part will be since the node to the tank 2 applying the power balance is obtained as the height of the node is equal to the height provided by the tank 2 plus losses. And the last part will be from the node to the tank 3. Applying the energy balance gives the height of the node is equal to the height provided by the tank 3 plus losses. Once made, the balance, along with the pump, we represent the equations. Represented the graphs. We turn to the second step. The second step would be to determine the feed and discharge curves. We said before that we had assumed the direction of the flow is in this part. We will see if we were right. With the direction of flow, first we determine the flow and the height. Food on the node only comes from the tank 1 flow. Then the height of the first balance becomes the feed height. Now calculate the discharge the node leaves. Flow to tank 2 and tank 3, then. And the discharge height is the sum of the last 2 energy balances. Once represented, feed and discharge curves, we look the cut point of these. As the cut point is below the curve of the pump is capable of delivering the flow in the direction we predicted at the beginning. If the cut point were above, we would have predicted wrong the direction of the flows, and we would have to start over. The last step would be to determine the layout and intersection curves. Once the cut point determined, we determine the flow and load height. Determine the flow. To calculate the height of the pump, we substitute it into the equation of the pump, and to determine the flows 2 and 3, we substitute the value of the height in the balance. Pipelines, which can be seen in all factories, houses, installations, etc. There are 2 types, branched and meshed. The branched pipes are easily solved compared to meshed, according to the method previously applied. only increases the complexity, due to ignorance of the directions of the flow. The meshed pipes cannot be solved by direct methods. In many places do not have no idea of the direction of flow, however have advantages over branched networks. Stability in H at the nodes, security against breakage. To solve them, apply Kirchhoff's laws, in which the elements are divided into meshes, branches, nodes, and the following conditions apply. The algebraic sum of flows in a node is 0. The algebraic sum of head losses in a mesh is 0. For installation, the operating point is the point that the energy supplied by the pump is equal to the losses dissipated. The operating point is unique, is well determined and fixed. If we want to work at a different flow rate, we cannot directly change the flow, since we would move along the curve installation, away from the operating point. We will have to change curve, modify the installation, will modify the pump curve. We will modify the curve of the installation, writing the energy equation in the usual way, being high, load height need not be constant. For example, a deposit at variable, but we cannot change at will, therefore we can only change the losses, which is achieved by modifying the steady loss of any single element. Let's separate the losses into two parts, losses that are caused by the throttle valve and the rest. Within the singular loss, the kV is a constant singular, which depends on the Reynolds, the roughness and diameter parameters we are not interested to change, and the degree of openness, which is simpler to change a pipe, for example. Then, by varying the valve opening, it moves through the pump characteristic curve, obtaining different points of operation at different flow rates. If we are closing the valve, the curve of the installation moves to the left, whereas if we open the installation, curve moves to the right. The second method of flow regulation is by varying the actuation of the pump. Consists of varying the RPM of the pump by changing the characteristic curve of the pump, applying dimensional analysis and assuming complete likeness. To calculate the point-to-point curve, we will use the equation. Observe that to obtain the set of points of operation of the installation, it is necessary to build different graphs pump and cut with the curve of the installation, as shown in the graph. To obtain the variation of the rotational speed of the pump can do, variable speed, gears, hydraulic coupling tubes, electric motors, variables, electrical, internal combustion gas turbines.